Hello, everybody. Welcome to one of the last sessions in this conference. Thank you for coming. Thank you for being till the end of this great event, which is now celebrating 20th birthday. And I was there at the first as well. So this session is about comparing predictive models, data science or machine learning models, but going beyond a single tool or a single language. So I will make a comparison of the same algorithm implementation within R, Python, analysis services, multidimensional with data mining, and Azure machine learning. So please silence cell phones and do explore everything PAS has to offer. There are a lot of free resources. Nice events are SQL Saturday, very nice, focused. And we have all kinds of possibilities also for you to volunteer and get involved with this work. I am Dejan Sarka. I come from Slovenia, Europe. I'm quite old already, a lot of time in this business, 35 years nearly, and I started as, I'm basically a mathematician, started in university and from 19th went to business, authored, co-authored 17 books so far, etc. So I will do a little bit of introduction and about introduction into the whole life cycle of this machine learning or any kind of advanced analytics. And then we'll start with simple ideas, yet later how to evaluate models, yet later this will become a little bit more complex. And especially we'll point out that it is very important to understand what kind of problems you are solving, because for different problems, different measures are appropriate. So it's not like one evaluation for every single case, valid for every single case. So how does it, what is the life cycle of a machine learning or data science project? So first you start by identifying a problem. So maybe you have just a simple marketing campaign, maybe you have some more complex problem, like you have some frauds, maybe with your credit cards, online banking, so you need to create a fraud detection system. So you identify the problem, and then you transform data into knowledge. So this is the part where you actually do this machine learning, starting with data preparation and preparing multiple models and then evaluating them. Of course, once you select the best model for your case, you act, which simply means you use this model somehow in production, whatever does it mean. So it might be as simple as simply check the results, view the results graphically, prepare the reports, or like for fraud detection, for example, build the model, make online predictions on every single piece of data that is coming into your system. Now, this looks nice, yes, but over the time, your models will deteriorate. So predictions will be worse over time. Initially, you might get very good predictions. Just think about fraud detection. Of course, fraudsters learn, so the patterns change, and you have to refine the model. So in order to realize when your model is becoming obsolete, you need to measure something, right? You measure, for example, actual and predicted frauds. And when the gap is rising, so less and less successfully predicted frauds, it means that you need to do something. So typically you store also predictions, not just the actual data, in some kind of data warehouse and analyze. And when you realize that your model is obsolete, you just identified a new problem and you start a new cycle, right? And now this transform part, this is where you actually work with data. So you start with understanding what is the problem you are solving, or business understanding and data understanding. So Do you have appropriate data to actually even analyze anything? And then you do data preparation, and then actually becomes this part where you implement different algorithms on data to create models. And then you evaluate models, so you decide which one will you use in production. And finally, then you deploy, which is, if you remember from the previous part, from the previous slide, the acting part of the life cycle. So I will focus on this small part, model evaluation, in this presentation. So for predictive models, and let's do, for a start, very simple predictive model, just predicting two possible values, true, false, yes, no, okay? Target variable, let's say, is binary. And for predictive models, initially, the idea how to evaluate them is very simple. You have your data with target variable state known, right? And you split the data into training and test set. And then you train the model on training set, and then you evaluate the models by predicting the target variable on the test set. And of course, since this is known data, you can simply measure how many times the predictions were accurate. So this looks very simple, and it is. It's not complex, of course. But the problem is that, you see, models will give you some accurate predictions and some false predictions. And let's say that we have this binary target variable, true, false, or yes, no. So you have four possibilities. A model correctly predicts state yes. This is called true positive. A model correctly predicts no. This is true negative. A model predicts yes while the actual value is no. So this is false positive. And of course, you can have also false negatives. So prediction is no while the actual value is yes. And now immediately you have to think, what is the business problem you are solving? Sometimes, all you need is just true positives. Let's say you have some kind of marketing campaign and you try to realize what kind of customers will be more interested in your product. So you will maybe mail them, maybe send some leaflets and so on. So all you are interested in are actually true positives. So there is no negative side effect if you have a lot of, let's say, false negatives. Nothing happens, not a big deal. I mentioned fraud detection. You see, with fraud detection, besides true positives, extremely important are false positives as well. False positives means, remember, you predicted something is true while it is false. So you predict that some transaction is fraudulent, but it's not. And why is this so important? Well, think about credit card usage. Turns out that, of course, the best customers are like using similar patterns as fraudsters. Like they do travel, they use credit card in a short time in multiple cities for maybe quite big amounts of data. Yes, because they are buying plane tickets, they are paying hotels, and so on. And this is very typical also for fraudsters. Now imagine, let's say you have a very good customer, which is in some foreign city, and the customer's flight was canceled, so the customer has urgently to buy a new flight ticket, and you cancel the credit card, right? You got very, very satisfied customer. So in this case, you see, true positives are important, but false positives might be even more important. So you might even decide to deploy a model that is not so good with true positives, but doesn't make too many errors with false positives. And something like 15 years ago, I was involved in an interesting project. We tried to predict landslides. So we tried to predict which areas are prone to landslides. And here suddenly false negatives were extremely important. Now just think of it. You predict there will not be a landslide. So people build houses, and then landslide happens, and people lose everything, maybe even die, you see. So suddenly, false negatives are extremely important, more important than anything else. So you see, this is how it starts. First, you have to understand your business problem you are trying to solve, and then you define which kind of measures will be important for your case. So, as I said, we start in a simple way, just split the data to training and test set, do the predictions, but then immediately we get more complex problems. Of course, it's important also that you do this split randomly so that there is no any kind of pattern built into this split. This is not a big problem unless you try to be over smart. So just use the tools like you have random sampling in R, you have random sampling in Python, in Azure ML, in analysis services. Just don't do it with Transact SQL. If you Google for it, how to get random rows, you will find a lot of solutions using new ID, right? Order by new top 10, order by new ID. So new ID is actually a GUID, and you know, GUID, what is the distribution of GUIDs? So each GUID has approximately the same probability, so it's kind of uniform, right? And what is statistically random distribution? What shape does it have? Bell curve, you see? So don't use this. This has nothing to do with statistical randomness, although it's a very popular solution. I'm just pointing this out. Use all of these tools that are specialized for statistics, for machine learning, of course, have built-in really random generators or statistical random generators. If you are not sure, you can test whether the split was random. So you can test, for example, take a continuous variable and check what is the first, let's say, population moments, like mean, standard deviation, maybe even skewness, kurtosis in training and test set. The numbers should be practically equal. If you do analysis of variance, test of means, test, you shouldn't get any significant pattern if you are not sure. But as I said, you can trust all of these specialized tools, just don't do it with T-SQL. Also, like in integration services, we have percentage sampling, row sampling. This is also using Windows API, Crypto API, and produces statistically random samples. Okay, now depends on the problem you are solving. You decide how you will represent the results of evaluation. So very simple representation is a leaf chart, which is extremely useful when you are interested specifically in true positives, specifically in one value, right? So imagine like marketing campaign. So here you see in leaf chart you have one line for each model, and then two additional lines. The topmost line is so-called ideal model line, which means in this case I use the target male view from the AdventureWorks ZW database, which has approximately 49% of bike buyers as target variable. So in ideal model with 49% of population, you would get 100% of target population or 100% of buyers. With random guess model, which is the bottom line, means if you select, let's say, 60% of people randomly, you will get 60% of all buyers. And the actual models are in between these two lines, so they show lift from the random guess line, and the higher the line, the better the model. So this is very simple tool showing you only one selected term, like true positives. Could be useful enough. Also, this tool has additional usability. You know, some algorithms, specifically for prediction, decision trees algorithm, and all derivatives like random forest and so on, tend to give you too good results to be true. This is called overfitting, right? Tend to develop so far that the results are simply too good. And with lift chart, it's easy to notice if the results are overfitting. You see, simply the line should never be horizontal. If this line of a model is not smooth, if it goes in steps, then it means at some part the line is practically horizontal, which means that you are at the ideal model. And this is not possible. At least at some parts of data, your model behaves like ideal model, and then you know that something is wrong, so you refine the model. Okay. So this seems very, very simple. Okay, but next possible test is cross-validation. So what is this about? Well, you see, some models might give you extremely good predictions, whatever you are interested in, right? False negatives, very low. Okay, great. They give you extremely good predictions, but only at this moment. With a small change in data, the quality of predictions might deteriorate substantially. This is not such a model is not a robust model. And maybe you don't want to use such a model in production, especially if you need to use it in longer terms. You know, like fraud detection is never-ending process. So robustness simply means that with small changes of data, the quality of predictions doesn't change much. And how do you test this? Well, now we have just training set, and then we split training set into multiple faults, for example, 10 or even 20. And then we use first fault for test set and the others for training. And then the second and so on. And each time we do the predictions, and then we measure what was the mean value of these predictions, but on the top of it, what was the deviation? You see, and if the deviation is high, then it means the model is not stable, not robust. So you might decide to use even a model that, again, gives you slightly worse predictions, but is more like stable. Now, to represent numbers, to represent this quality of predictions with numbers, you simply create classification, or also called confusion matrix. So you have predicted and actual values, and then you have, you see, in the bottom right corner, you have true positives. In the top left corner, you have true negatives, and so on. And you have these four numbers. Even visually, you can already maybe compare some models. For example, if you are interested in true positives, so only simply the higher number in the bottom right corner, the better the model. Okay? Then it turns out that you can calculate many different terms out of these four numbers. And yes, many of them are defined. And for this and couple of next slides, and especially also for calculation I will do later in code, I really spent a lot of time not to confuse something. So I'm pretty sure it is correct. I'm pretty sure I went through it, I don't know how many times, because it's so easy to mix something. So all of these terms have a name. This is very typical in statistics. You know, people try to get known with invention of something, so they, do another calculation that nobody thought of with these numbers and have another name, and they go into history. Although nobody remembers who they were anyway, but at least it's a good feeling. So recall, hit rate, sensitivity, true positive rate. These are just the names for this calculation. True positives divided by true positives plus false negatives. So you see, for example, for landslides, this could already be much more useful measure than just numbers or just showing this in lift chart. Specificity, true negative rate, true negatives divided by true negatives plus false positives, maybe also for landslide. Positive predictive value precision, true positives divided by true positives plus false positives. This would be probably a term more useful for fraud detection. And then we have negative predicted values, true negatives divided by true negatives plus false positives. False negative rate could be, remember, extremely important for landslide. False negatives divided by false negatives plus true positives. Fallout, false positive rate important for fraud detection again. And then we have false discovery rate, false positives divided by false positives plus true positives, false omission rate. It's not really important that you know the names, but since these are the official names, I'm using them, right? The point here is that you must find which measure is appropriate for your problem. And you see how many ways you can combine just 4 numbers. Very good one is this one, very popular, accuracy. Simply correct predictions, true positives plus true negatives divided by the total number of cases in the test set. Harmonic mean of precision and sensitivity, true positives divided by multiplied by 2 and divided by true positives multiplied by 2 plus false positives plus false negatives. This is kind of very useful measure for complex problems that combines all of these terms and gives you the overall idea, not just a little bit more complex idea of overall quality of predictions, a little bit more complex than accuracy. Very popular is also this kind of presentation, ROC curve, receiver operating characteristics. So this is plotting true positive rate against false positive rate. And again, the higher the model, the better the score. So for example, this is something that is very useful for fraud detection. Looks like leaf chart, but is more complex, right? And okay, now we have the idea what we need and how do we get it? And of course, how do we get it all together then? So I will show you some models in starting with the good old analysis services data mining and going through R and Python and Azure machine learning. And we'll show you how you have how are implemented these different measures within these different tools and languages. So first of all, with R and Python, of course, these are programming languages. So if something is missing, you can always add it, right? There are many things out of the box, but anyway, you can always do whatever you wish there. So in Azure ML, we have quite a lot of terms from classification matrix. We can see receiver operational characteristics, and in chart and in analysis services, we have leaf chart. Classification matrix is extremely basic, but it has also possibility to automatize cross-validation. Now, let me show you my data and my projects. So first of all, I will not go into details, but I just used SSAS to split the data, right? Integration services to split the data into 70% training set and 30% test set. By the way, there is no strong mathematics behind what percentage of data should you use for test and what for training set. Usually people simply use 70-30, some even 80-20, some even 50-50, you will see sometimes. Anyway, there is no strict mathematics behind. Depends also on the amount of data you have, right? Okay, this is, I just created 2 tables and also multicasted to comma-separated values files, so I could also upload them in Azure ML. Okay? This is nothing special, but then I created a mining model with analysis services multidimensional data mining. It is not by far, not even comparable to what you get nowadays with R and Python, of course, but might be also still useful for a starting point because you can easily create models without knowing how to program, without learning a new programming language. Of course, it is limited what you can do, but not everybody needs a complete new language. Like if you start studying R, then you definitely want to go to this data science direction because this is what R is created for. And it means you have a huge investment in time and money to get to some results. Sometimes, as I said, maybe you need just a simple marketing campaign, or maybe some simple association rules. Then analysis services could be good enough. So here I have my data source. In my data source view, you see I simply transferred data from SQL Server training and test set, right? And on the top of it, I defined mining structure and mining model. So in this case, I'm using this target mail view, and my bike buyer column, the second from the top, is predictive. All others are input, of course, and customer key is the key. And I'm using naive Bayes or Bayesian inference algorithm. I will use the same algorithm in different tools. So we will see how the implementations might differ. Anyway, here you can see this is the limited list of algorithms supported by analysis services. So really just a few algorithms. Most of them are very well implemented, so it might be still useful because, as I said, not everybody will start to learn a new programming language just to do some simple model. And on the top of it, we have very, very nice viewers. So it's kind of easy to understand the models. So analysis services has very nice graphical presentation of these models. So here you see influencers, what influence the decision to buy a bike. And you can see that the most important thing is number of cars owned for this model, then total children, then commute distance, etc. So we have also other viewers. So for example, this one is nice attribute discrimination. So you can see what favors value 0 and what favors value 1, which is bike buyer. So 0 cars favors buying a bike, 2 cars favors not buying a bike, and so on. Anyway, we have this mining accuracy chart tool. So I will simply use different data set, the test set, and this Visual Studio Designer is actually creating for me DMX query. So there is a programming language behind, very simple one. DMX looks like very simplified T-SQL. Okay. Anyway, the join was created, right? And automatically for me. And I am interested in this case in true positives only. So I can easily get a lift chart and measure lift from the random guess line. Anyway, I can go to classification matrix. If I want to compare between different tools, I will use classification matrix. And you see like true positives, true negatives in top left corner, and false positives, false negatives. Of course, so we have these numbers prepared. Nice. Of course, we have no idea what does it mean at this moment. Right? Because we need to compare multiple models, then we will have the idea which one is better, which one is worse. But here is how you get to these numbers with analysis services. Now, I prepared some models in Azure ML. So again, I used Azure ML implementation of naive Bayes algorithm. So two-class Bayes point match machine, Bayesian inference. And of course, I trained it, you see, on my training data, and then used test data to score the model, which simply means score the model means adding predictions. So now I have, besides original data, I can visualize this. So besides original data, I have also the score. So you see last two columns are scored labels and scored probabilities. And you see, like, if you go to the left from scored labels is the actual value of bike buyer. And you see that, like, first row has a true positive, second and third row are false positives, and then we have true negative. And evaluation, you see this, let's say, element, this can show you the ROC curve, so we can compare false positive and true positive rate, right? Again, we would need to have multiple models just in Azure ML, but if I want to compare the quality of this model together with analysis services, then I can go to classification matrix. So here I have true positives, true negatives, and also you see some of these terms I mentioned also calculated. Overall accuracy, precision, recall, F1 score. Do you still remember the formulas? I wouldn't be able now to repeat all of them without going back to slide. I'm losing the microphone. Got it. Okay. Now, okay, we can already visually compare the results. And maybe you notice that accuracy is slightly better in Azure ML. Not big difference, but there were more than 1,800 true positives and more than 1,800 true negatives. Okay, so at this moment it looks that Azure ML is slightly better. Of course, it's much younger implementation, but you see that also analysis services implementation, although it comes from year 2005, is still working quite well. Now, let me switch to R, and let me put this in pocket. Maybe this will be better. Let me switch to R. So I will connect to my SQL server and read the data. And in this case, first of all, I will union all data and split it then back in R. So why I'm doing this, this sounds a little bit ridiculous. You see, I have training test set, so I'm doing union just to split it then back in R, okay? Does anybody has an idea why am I doing this? But I will just use this split which is already there, because I want to have the same data I had in Azure ML and the same data that I had in analysis services. There is one thing. Later, I will use this code inside SP execute external script to execute it from SQL Server. And this procedure that executes R, Python, or in 2019 even JavaScript, right, has these parameters: language, the actual script. So this is the actual R script, copied and pasted from RStudio. And then it has, you see, parameter input data 1 and input data 1 name. And this might lead you to a conclusion that you can have also input data 2, but it's not true. So here we are limited to a single input data. So that's why I'm unioning this data and splitting it back in R, because I cannot feed this procedure with two queries. Okay? So let me just read the data, close the connection. And of course, if you go with tools like R and Python, it's very important to properly prepare data. So to define in R, let's say for these discrete variables, in R they are called factors, to define correctly the order of levels if they have some internal order, like, you know, education has some internal order. Otherwise, you might get worse results or even spurious correlations, which have nothing to do with real life, right? And this is pretty dangerous, because it's a very frequent mistake that people forget to do it, you know, and then rely upon results, while there would be better to use rule of thumb, you know. Anyway, so just to check if this is, you see, even like this, discrete variables, even if you make a bar chart, it should somehow resemble Gaussian distribution. If it's kind of weirder, then it doesn't look well. Now I'm simply splitting it back to training and test set, and I will use naive Bayes algorithm implementation from package called E1071. This is very popular naive-Bayes implementation in R. There is one thing worth mentioning. You see, in R, rules for adding libraries are very relaxed. So, for example, there is no naming convention. So, like, would you search for naive Bayes algorithm in a package called E1071? Right? So, of course, in this case, Google is your friend. Otherwise, it's impossible to find out where are the things that you need. So, I will use this naive Bayes function from this package E1071 and define the target variable, the variable on 13th position in the training set, and first variable, first position is the key, others are input. Now I will simply add predictions with predict function, and model is here, model is created, you see. And here is also, you can see what is the content of the model, etc. Anyway, I will use function predict, which I will feed with the model and test set and perform what is called raw predictions. And then simply bind them back to the original data frame using column bind function. You see in R, these data frames look like tables, right? But they are not tables like relations in relational sense. They are matrices, so you can rely upon order. Order is maintained. So I'm simply binding the results by columns. So first row of original data with first row of results. And I know it will be bound correctly. Now I can simply view first of all, I need to execute this. That's now. Okay. Now I execute it, so now I can bind them and see like original data and raw predictions in terms of probability for each state. So this was like naive Bayes prediction in R. So you see original data, customer key 11001 is actually a buyer, and we have like 67% probability that this is prediction that this is a buyer with 67% probability. So this is again a true positive. And the second one is also a true positive. Fourth one is just a little bit over 50% that is true negative. Okay? So what is the overall result? So let's make a simple classification matrix. And you see here are the numbers from R, right? If you look only at true predictions, it looks slightly worse, just like over the quick glimpse, slightly worse than Azure ML. But we have actually a very low amount of false negatives in this case. So you see, although it looks at the first glimpse worse than it was in Azure ML, worse than even in maybe analysis services, it really depends what you are searching for. So in this case, this model is very good for false negatives. Okay, so this is, I can also store this in a table, in an object. And finally, let's go to Python. So I will use some Python libraries, OWC. NumPy is the basic library you need for matrix operations. You know, R is specifically designed for statistics, so matrices are built in the core R engine. You don't need any additional library for this. Python doesn't support vector matrix operations out of the box. NumPy is the library that is like basis for any other statistical or machine learning analysis. And then on the top of NumPy, we have Pandas library, which brings the data frame object. So Python is simply copying copying logic from R. So it's actually the same thing as data frame in R, just implemented in Python. And then we have sklearn or scikit-learn. For example, there is nice function accuracy score, and we have naive Bayes, Gaussian naive Bayes mining model. So just a couple of libraries, and you have everything you need in Python. So now I will connect again to my SQL Server database, read the data. Again, the same reason as in R, why I union the data, you see, and then I will simply split it into training and test sets. But also all of these functions in scikit-learn need to have input matrix and target vector. So target variable must be taken out as a separate vector. So I will first split the data using this variable I got from SQL Server. And I will split it into training test and test set, and input variables for training set and target variable in a vector form. And the same thing for the test set. Okay? So I have some input variables, and my target variable is a single vector. Okay? Now I will simply call the create a model using Gaussian NB, and with model fit function, I'm actually doing the training. And now I have predict function that I can use for predictions, right? And these are predictions, 5,546 cases, right? And this is with a single predicted variable. For example, in Python, I can just calculate accuracy score, right? You see again, it was slightly lower than in Azure ML. I can also add this data to my output, right? And I can get, again, this data together. So with actual values, so you see, like in this case, with Python, the customer 110001 is false negative. And now you can compare these things, right? Okay, so how do I get this all together to make some comparison? So I will turn to SSAS again. So I have another package that will actually in my data flow get all of these things together. So simple as that. So I have first data mining query. So I'm reading the test data from SQL Server. You see, this is my test data. And I have data mining query transformation, which is actually creating this thing. Let me copy it. So I will show it here. And create a new DMX query. And select appropriate model. So this is how this query actually looks like. So this is the DMX query. So it has prediction join, input row set is my test data, right, like variable, and then I'm joining this to the model, and I'm adding the predicted value. And then I'm simply adding a derived column, which will be a string. So I will know that this row came from analysis services. Now, for R and Python, there is no direct possibility of executing R or Python code. But what we have is this, right? We have execute external script. Remember, because of this procedure, I had to union data just to split it then back in R and in Python. And this is like R code that is executing. at this time from SQL Server, but of course you can use the same code in integration services. So I'm just using SQL Server OLEDB source, and you see this procedure will be executing and will return exactly this row set. You see, exactly this row set. So next thing is again derived column. In this case, remember with R we got raw predictions, so just probability for target states. So I want to get the labels yes, no. Okay, so I have two derived columns, and of course source is simply constant R. And same thing for Python, right? So this will be executed again in SSAS. Just Python will, if you remember from Python, will already give me the labels, actual and predicted. So will be less derived columns needed in SSAS. Right? So this is from Python, sp execute external script, and here is the derived column, which will just tell me that this comes from Python. Finally, how do you do Azure ML predictions? So what you must create from a scored model is a web service. So I created this naive-Bayes classification for bike buyer, right? And here is what you can do. This is how you connect API key, right? This is how you connect from your code. And here you can test already the model. Test means just manually test predictions on a single case. So for example, let's say this will be test set, whatever, or train set. Customer key is not important. Let's say that we have a married person. Let's say that this is female. Okay, maybe with one child and one at home. And let's say that we have some bachelor's degree. Occupation, let's say professional. Owns a house, has one car, let's say. Commute distance, maybe 0 to 1 miles. These values, yeah, I know them. These values should be the same as they are in your data, otherwise join will not be performed correctly. It will be join, but not using all input variables, so predictions will be false. Let's say that this is from Europe, this person, age with one child, let's say 35, and income maybe 80,000. Okay. And okay, that's it. And now I got, okay, so this is predicted 1, but with the last column is probability a little bit over 50% for this data. Now, here you have also code for batch execution. So code for batch execution, and you have actually code prepared, how do you call this, with different languages. So you see, you have code in C#, in Python, in R, prepared, how do you call this, and feed it. Okay. Anyway, I find the best possibility. Here is already a little bit out of date in Azure ML. There is a nice R library called Azure ML, which simplifies this code a lot. So the simplest way how to call Azure ML models is nowadays from R. Anyway, I was not sure whether this web service, whether web would be available. Typically on such conferences you have bad connections. So just in case, if you go here, remember we have also possibility to do this in Excel. So actually there is Excel Azure ML add-in, and if you click here, you will get simply an empty Excel file with this add-in installed. And then you simply read some data, and I actually already did this. So this is my Excel. I already prepared it in advance, so I have it locally, so I don't need to rely upon web connections. And here we have, you see, this is the training set open in Excel file with bike buyer column and scored labels, scored probabilities. And these are the same numbers as you saw. Remember where? Here, score model. When we scored the model, scored labels, scored probabilities. So this is actually the same thing, just in Excel with Azure ML add-in. Okay. So we are all set. And the last thing is just to bring everything together and store this in a SQL Server table. Now here, it looks very nice, but there is one thing. Sometimes, you start using something and you are very excited, but then might be some disappointment comes. What is the problem here is, remember, SQL 2016 brought a new service, Launchpad service, which is actually communicating with external engines with R and Python. And this is practically single-threaded engine. So simply I should either execute R or Python, or simply split this in two data flows and then execute R or Python. I will just try to execute. I said practically. The worst thing is that sometimes it works, sometimes it doesn't. Okay? In most of cases, it doesn't. So let me just execute this package, and let's see. I have also prepared, you see, additional data flow and so on, and disable it. And yes, unfortunately, this one will work in any case, but don't worry. I have, what is this truncate table? This will work, right? So first I will destroy whatever I already have there. And if it doesn't work, I will have an empty table, but I have a backup, of course. So let's go to data flow and see if it will work. Let's execute it. And sometimes it's simply stuck here because Python and R code calling this service, they are locking them out. So if I just drop something, it's already too long. It's already too long. I think this time it will not come through. Okay, let's just stop. Don't worry, I got backup. So I will just, for a second, delete, let's say, Python in this case. Try to execute the task. And it's still somehow locked. You see, now immediately works. And now, of course, I could add Python and so on. Right? But sometimes even works in multi-thread. I don't know. I didn't figure out exactly when and how. Anyway, now I have half full this table, right? So let me first get this back. Go to control flow and empty it. So it's empty again. And now let me go to SQL Server. And you see. So first, this table should be empty, right? But I have a copy from the moment when it was full. I created a copy. So now I can insert data back from the copy. Fine. So pretend that my package worked. Results are here. And here are the results. You see, so I have actual predicted value for each customer, and I have source. So now it's just a matter of a couple of queries and calculations. So I will simply pivot this to get true negatives, false positives, false negatives, and true positives. So now I have everything I need for each source in a single line. You see, aggregated over columns and rows. Now you can already compare these values. And maybe you notice something. They are quite similar, the values, except interesting for Python, you see. For Python, we have much, much better result in true positives, but unfortunately, much worse for false positives. It's interesting because, you know, for me it was a little bit of surprise because naive Bayes is a very simple algorithm. And it's interesting that with different implementations, you can get different results, you see. It's quite a simple algorithm. And now this part was the hardest. So remember all of these things from the slides. And yes, here are all of these calculations in a single query. Here are all of these calculations. Of course, I will upload the code as well, so you will be able to check by yourself, right? If these calculations are correct. I'm pretty sure they are correct. Also, like I went from slides step by step, one at a time, because there are so many, you know. And now, of course, you can compare these models, and even better, of course, I already created, for example, Power BI report. So we introduce another tool, Power BI, for this, right? So, and show these values graphically. What also we will see also in this Power BI report the same thing as we saw on numbers, right? The models in different implementations are pretty similar, except somehow Python is always somehow special, you see. Python is always somehow either bad or very good. Others are much closer together. But of course, you can also see in the numbers. So this doesn't mean some implementation is better, some is worse. It just means that some implementation fits better to some problem. And please understand, people ask me, so what would you now recommend, R or Python? No, it doesn't mean, you know, we have just compared one algorithm or one implementation. I mean, like in R, you have 10 different implementations or more of naive Bayes, and just a single algorithm. Then, of course, you should go with decision trees, you should go with logistic regression, with neural network, analyze the same data before you decide which one is the best. But if we would select among these four models, let's say for some marketing campaign, I would go with Python, right? For maybe fraud detection, in this case, I would kind of Azure ML is also very good, like for fraud detection. So we see we have a lot of true positives, a little bit less than in R, but we have much less false positives than in R, you see? Analysis services, false positives also very good, but true positives not that good. So let's say like for fraud detection, I would probably go with Azure ML in this case. For marketing campaign with Python maybe, etc. You know, so it really depends on the problem. Don't conclude that what R is better or whatever is better. Okay? Don't conclude. Exactly. So the question is R versus Python. Yes, it really depends on the library. So we have multiple implementations, right? And one can be better, one can be worse, right? Okay, for binary classification, which would be my favorite? Probably decision trees. It's very understandable, and usually gives very good results. Usually good, very simple. Like neural, again, as I said, depends if you need to understand. You know, I would say like, what is big difference between data mining and machine learning? With data mining, users are people. So you want to understand how did you get there. Then decision trees might be the best. For machine learning, you don't care how you got there. The only important thing is how good predictions are. So maybe neural networks would be better. But for business problems, you know, in business people, we are not so complicated. You know, decisions are based on a couple of input parameters, and that's why decision trees are very good, because they are easy to understand and simple to interpret and so on. Neural networks or deep learning, where you have I don't know how many layers, impossible to interpret how. Sorry? Yes. Yes, especially like for these simple decisions, will you buy something or not? Think of it, how do you decide? You don't take into account 500 parameters, right? First you look at your wallet, can I afford this? And so on, you know, couple of parameters, basic, very basic ones. Yes, please, yes. We are exactly at the time for question because we are at the end, so please. Sorry, I didn't hear. Can you come closer? Okay, so if you have this huge data sets, right? Then definitely you can use this RevoScale R and Microsoft ML libraries. RevoScale R has very nice implementations also for these selections, and is highly parallelized and much more efficient than any other R library. And you have also RevoScale Pi, so it's transferred to Python as well. But unfortunately, not all functions, especially this with data preparation, are implemented. So in this case, maybe the best solution would be RevoScale R, Eric's get data, I don't know, Eric's some function, very, very powerful with many parameters, and highly, highly scalable. Also, you know, just to give you the idea, let's say if you would have really billions of rows, then you have a problem. No, I mean, you know, this, even RevoScale R, nothing in R, nothing in Python can compare to Transact SQL when we talk about data. Now, SQL Server Database Engine is specialized for dealing with data, not with analyzing data. Unfortunately, it's kind of hard to get real randomness there. But it's doable. But if you, as I said, if you really have to deal with huge data sets, none of these tools can compare to database engine. So after all, we are back to basics. You know? No, seriously, you know, these tools are created to work with statistical functions more. And in statistics, typically you do work on samples. And by the way, just also to mention, it is also a misconception that the more data means better results, more accuracy. It's not true. It really, again, depends on algorithms. So the vast majority of these machine learning algorithms are actually tailored to work on samples, not on huge data sets. For example, clustering, you know, you are searching for clusters. If you have too much data, too many cases, you will get what is called local maximums. Some very, very, very well identified groups, but they are accidentally cases together. And they are maybe overrepresented. Yes, yes. Actually, let's say not completely randomly. This is called like stratified sampling. So if you have, I don't know, like 30% of people in high school in overall data, you want to also have 30% of people in high school with high school in your sample, right? So it's random across multiple variables. Yes, please. Okay, so we have this issue, which might be very, very frequent in business. For example, in fraud detection, hopefully the number of frauds is small, so target value is rare. Typically, you have like 0.5, 0.7% of transactions are fraudulent. And then it's kind of hard for models to learn if the target state is represented so infrequently. So what you can do in these cases, people do either multiplying this, you see, like overloading this target, multiplying this target values multiple times, or undersampling simply if you have enough rows, and this is very useful for fraud detection, undersampling. So you create a sample where you have, let's say that you have 0.7% of frauds, but you have like millions of transactions per day, so you have enough data. So you create a sample where you have 7% or maybe even 20% of frauds by simply selecting less non-fraudulent rows. But also you have to test some algorithms are more unstable, like neural networks are typically very unstable when you have very low amount of target values. Decision trees are simple, so usually the simplest the tool, then also the more stable is. So decision trees are simpler and they're typically more stable, also on iOS. Again, this doesn't mean better. Okay. Okay, what is the sample size? Let's say from statistics, you see, you don't need even 100,000 cases. So you can go with anything between, like in statistics, like they call big samples already start with 200 and more cases, which is then you cannot be, so the predictions, you know, the confidence level is very low. But you get high confidence level in predictions already like with 15,000 cases. So anything between 15,000 and 100,000 is okay. Unless you have this problem that you have target state very infrequently represented in the data. Yes, please? Yes, yes. Those are the numbers for the training. Yes, please? Okay, I didn't work with insurance, but I actually worked a lot in fraud detection with many banks and credit card issuers. And yes, I was just selecting a model that is simple and implemented in all basic libraries. So nowadays, you know, the quality of predictions, nowadays is probably the simplest model. Nowadays, because it doesn't even take into account that input variables might be correlated. This is where the naive word comes from. And so typically you get better results with more complex algorithms. But I just wanted for this example to have something that is simple enough to see the what is the difference in implementation. Also, yes? Let's say if it is sampling, if it's random and data didn't change, then you don't need to do all of the modeling. The problem here is, how do you know that you got the best model? You don't know. You don't know. You simply define the time. I will spend 2 weeks, and that's it. And then you go in production, but then remember the whole life cycle, then you measure. So you can also try later with additional models. But this is one of these things which makes any kind of such project hard to sell. Managers will ask, will we guarantee that we get the best model? I have no clue. I always recommend with predictive models, just if you don't have it something in place, just create a small data warehouse and simply load it all of the time and just check it occasionally. But you have every day, you have a load also. You don't need to load, like for frauds, you don't need to load million rows. You can, again, just load the sample. But you do it constantly. Yeah, I think this is the best, and you maybe even can have some alerts if the quality falls under some specific level. But also once you have this infrastructure, it's easy to constantly improve, not just wait until the model deteriorates. Maybe you can try, maybe you find some new library. Like in R, we have 13,000 libraries and more. I don't know all of them. Maybe, just the next one you would take, you would get much better result. This is. Yeah. Okay, this is it. Any other questions left? We still have like 3 minutes. Yes, please. There was Dorian Pyle, Dorian Pyle, is a good writer that wrote some books how to select appropriate technique. Also, Gordon Linoff and Michael Berry wrote about this. But one thing that is very, very interesting in this area, let's stay with fraud detection, which I know very well. There is not much things published. This is secret. So unfortunately, those who do this, we don't share information. So many times we have to reinvent the wheel. Yes, but Dorian Pyle and Gordon Linoff and Michael Berry wrote a lot of things how to also select appropriate model and appropriate measure. The selection of this data is just basic. It has to be random, right? And then it's you can calculate some statistical distributions, like statistical moments for continuous variables. So they should be, if this is random, they should be approximately the same. Otherwise, some sampling is biased. Okay, I guess people are leaving. So thank you very much. Please stay for the last session. Thank you very much.